Stop building a Ferrari when you need a skateboard. Meet ordinary least squares. Training this model doesn't need trial and error. It can be trained using just one line of linear algebra. It's not flashy. It's not the hottest new thing on Twitter, but it's reliable, easy to understand, and honestly, in a lot of real projects, it's exactly what you need to start. The Toyota Camry of machine learning models. Welcome to Schovia, where we make AI concepts feel like everyday ideas. Today, we are talking about ordinary least squares, OLS. Let's start with talking about your data. You may have a table of data. Maybe it's sales numbers, maybe it's housing prices. You have rows, which are the examples, and you have columns, which are the features. You need to predict a number in the future, like the sales or the house price, given some information about the market. Your instinct might be to grab the fanciest, newest AI tool that you saw on Twitter. Don't. Let's start with a simple example of a table with 4 columns. Each row here represents a market or a region, and sales column represents how many units it sells in that market. And the rest of the values represent the amount of money they spent on each type of advertising. You'll see that you can apply this technique to bigger tables as well. Let's look at the math, but think about it as a recipe. The model assumes that your sales are just a weighted sum of your spending, which means that your prediction of sales is equal to a weight allocated to everything that you spend on TV and the weight allocated on how much you spent on radio, plus a baseline. So the cool part is that these weights are actually telling you a story. If the weight for TV is high, it means for every dollar that you put in, you get a lot of sales out. That's your ROI. If the weight for newspaper is nearly zero, it means that the channel is deadweight. You're spending money, but it's not moving the needle on sales. And that baseline B that you see here, that's your intercept. That's how many units you'd sell if you spent $0 on marketing. Maybe people just walk by and buy it anyway. So OLS doesn't just give you predictions, it gives you interpretable knobs that explain what's going on. But that raises a big question. How do we find the best weights and the baseline? So, to pick the best weights, we need a scoreboard. In supervised learning, that scoreboard is called a loss function. If your predictions are bad, the loss is big. If your predictions are good, the loss is small. We want that number to be as low as possible. For OLS, the loss function is the mean squared error, also known as the MSE. And here's the idea. For each row in your table, you make a prediction. You compare it to the true sales. You look at the error, where the error is essentially the difference. And then you can square the error and average it across all the rows. Why square it? Why not just add up the mistakes? That's because we want to punish the big mistakes much harder than the small ones. If you predict sales and if you're off by 1 unit, square of 1 is equal to 1. That's no big deal. But if you're off by 10 units, then square of 10 is 100, which is large. So the penalty explodes. So OLS chooses weights that try to keep these squared errors small on average. The model becomes afraid of huge misses. It's willing to be slightly wrong in lots of places if that helps it to avoid being terribly wrong at any one place. You can picture it as drawing a line or a plane or a hyperplane through the data that is safe overall rather than perfect for just a few points and then terrible for some other points. So now we know what we are optimizing, and we need to find the weights that minimize the mean squared error. So the next question is, how do we actually compute these weights? In more complex models like deep learning, the computer has to learn slowly, trial and error over thousands of steps. But for OLS, we don't need to guess. We have a closed form solution, which means we can literally use algebra to find the mathematically perfect budget mix in one shot. This formula is called the normal equation. If you're comfortable with linear algebra, this is how it looks, where this term is your data matrix and y represents the vector of sales. And what you're seeing here is a transpose of it being multiplied with it. If that felt like jargon soup, don't worry. Here's the intuition. You plug your table into this formula, do one big matrix calculation, and as a result of that, you get the optimal weights that minimize the mean squared error. So there are no loops, there's no guesswork. It's just one big calculation, and you know what the ideal model weights are. If you think about it in terms of code, what you need to do is build your X matrix and your Y vector, and the solution is literally just 3 lines of code. I have posted a link to a Python notebook in the description where you can load a simple advertising and sales dataset and build these matrices, run exactly these 3 lines, and you can see the learned weights and the baseline. Running this example will help you to connect the table with the formula and the mean square error loss. So OLS is a great starting point, but it's not magic. If you have too many features, or if you have features that are very similar to each other, or you have a lot of noisy data, then OLS can overfit, which means it tries too hard to perfectly match the training data. And it ends up making worse predictions on new data. That's when we add guardrails called regularization, which can be of type ridge or lasso, etc. Regularization gently pushes the weights away from these extreme values, so the model generalizes better. We'll dive into those techniques in the next video. For now, the takeaway is that if you have a table of examples, columns of numeric features, and a numeric value that you want to predict, don't start off with a giant neural network. Start with OLS. It's simple to code, easy to explain to non technical teammates, and surprisingly powerful as a first baseline. Thanks for joining us on Schovia Labs. If this helped you see OLS more clearly, hit that subscribe button, share this with a friend, and as always, stay curious.